Hi, everyone. Thanks for joining me. This is Meghana from SigOpt. I'm an ML engineer here, and today we're just going to go over some ways to efficiently create image classification models and techniques to use to help do that. This is going to be a webinar based off of my talk from MLConf this year. Great. I hope everyone can hear me. I guess we'll find out if people can't. I'm just going to give people a couple more minutes to join and we'll just get started since then. And I'll be taking questions at the end, so yeah. Okay, we'll go ahead and get started. So as I just said, today we'll be talking about how to optimize image classification models on the cheap. So we all want to build the best possible models. And ideally, that would mean that all of our models would be trained till the end of time on all the data that is in the world related to our problem, and we'd iterate through every single possible model configuration that makes sense. But we can't really do that due to constraints we have to consider, including compute constraints, time constraints, and our general sanity. So given these constraints, how can we build the best possible models when long training times need to be taken into consideration and are a problem that we want to solve given these constraints? So today we'll be looking at 3 efficient techniques that help us do this. One, we'll be looking at transfer learning to reduce our training time. 2, we'll look at multitask optimization to reduce our tuning time. And lastly, we'll look at black box image augmentation to efficiently increase our model performance. So as I said, we'll be using transfer learning to reduce our training time, multitask to reduce tuning time, and black box image augmentation will be used to increase our model performance. So before we jump into our use case, let's just take a look at an overview of these concepts to make sure we're all on the same page. So we'll be leveraging transfer learning. There are many ways to do transfer learning, and today we'll focus on fine-tuning and feature extraction. In both cases, we'll be using a pre-trained ResNet model on ImageNet 1000 to initialize our model weights. In fine-tuning, we will tune the whole model, including the convolutions and the fully connected layer from the starting point of our pre-trained weights. And in feature extraction, we'll use the pre-trained weights to transform our input data into key features, and we'll only tune the final fully connected layer. So we will use image augmentation to boost our model performance with minimal cost. The augmentation process will go through classic techniques such as horizontal flip and random cropping. And we will play with color jitter as the main augmentation technique that we consider. Specifically, we'll be looking at how parameters involved in saturation, hue, contrast, and brightness affect our downstream classification performance. Before jumping into multitask optimization, let's take a gander at what an optimization loop looks like in general using SigOpt. So we'll be using SigOpt as our multitask optimization platform. In a single optimization loop, SigOpt will provide hyperparameter suggestions for stochastic gradient descent. Our ResNet model is trained using these parameters, and we return the model's validation accuracy back to SigOpt. SigOpt will then use this validation accuracy to intelligently sample from the hyperparameter space to provide a new set of stochastic gradient descent parameter suggestions. So essentially it becomes this iterative process where we go through this loop multiple times, and over time we should see our model's performance getting better. We'll run this process in parallel as optimization, as I'm sure all of you know, takes a really long time. So now stepping into multitask optimization. Multitask optimization really starts with a very simple idea that partially trained models can be leveraged to inform hyperparameter tuning of fully trained models. So essentially, if we can learn from partially trained models and apply those insights to fully trained models, then we can collect information about our model at a reduced cost. So now we're looking at an example from Klein 2017. Here, Klein trains an SVM model on the MNIST dataset. These charts show how the performance of the model responds to changes from a regularization parameter and a kernel parameter for the SVM algorithm that Klein uses. So really what Klein is doing here is the team is defining this partiality, and this partiality really comes from subsections of the data. So going from left to right, you see we have a very small portion of the data to 1/16 of the data set to 1/4 and the full data set itself. And what's happening here is the partial data sets the models are trained on these partial data sets, and we get this idea of like what the hyperparameter landscape looks like, where we can see what we learned from the smallest subset of data, the blue portion, is actually transferable to larger sets of the data and is completely transferable to the full data set as well. This means that we can learn about our fully trained model more cheaply by sampling observations from the partially trained model. So today we'll be looking at how to leverage these 3 techniques to efficiently build high-performing image classification models. We'll be classifying the Stanford Cars dataset. The dataset is composed of around 16K images and 196 classes. Apart from the low number of data points, this dataset is particularly challenging as each of the 196 classes is only around 0.05% of the data, so each class is not highly represented. And the labels themselves for the data points are very close in the label space. And what I mean by this is that not only does the model have to accurately identify an image of a car, it's a Honda Accord, but it also has to successfully distinguish between a Honda Accord 2011 and a Honda Accord 2012. So these properties make this data set a really great benchmark data set for image classification. We'll be using ResNet as our model architecture. Once again, we'll be using multitask optimization as our hyperparameter tuning strategy. As we saw in Klein 2017 in this image, there's this partiality that is leveraged to train and inform partially trained models to fully trained models, which means that we have to define this partiality. So instead of splitting up our data set, we'll define partiality as the fraction of the total number of training epochs. So low-cost tasks will be 10%, medium is 50%, and full is 100%, with 35 epochs being our full number of training epochs. What we should see from this optimization strategy is low-cost tasks will first be populated in the hyperparameter space, exploring the space generally, followed by a peppering of medium-cost tasks and full-cost tasks only coming in when the strategy is confident of a region in the hyperparameter space that is optimal for the problem. So this is our experiment scenario. We will be comparing transfer learning techniques against optimization, the effects of optimization. So we'll use ResNet 50 for feature extraction and ResNet 18 for fine tuning. These model depths were chosen to keep compute costs down and to explore model performance of different model depths. So essentially we'll be trying to understand which transfer learning technique works best for our data set and how effective optimization is on top of that. So just a reiteration, ResNet 18 will be used for fine tuning and ResNet 50 will be used as a feature extractor. The deeper network was chosen to be the feature extractor as deep deeper networks have classically been better at identifying important features in the data, and the shallower network is also faster and cheaper to fine-tune. So why those decisions were made. We'll be hyperparameter tuning all the parameters for stochastic gradient descent. So jumping into what our optimization looks like. So we kind of went over this in the beginning, but just as a recap, so SigOpt's multitask optimization will suggest our stochastic gradient descent parameter suggestions. We'll train our ResNet model and then return its validation accuracy. The training is done on 80% of the data, and the validation is performed on 20% of our data set, and each class is equally represented across this training validation split. So what did the results look like? If we just take a look at our transfer learning comparison, we see that fine-tuning a shallower network, our ResNet 18, significantly outperforms using a deeper network, ResNet 50, as a feature extractor. And really what this shows is that our data set, the Stanford Cars data set, is very dissimilar to the pre-trained ResNet 18 on ImageNet that we leveraged to initialize our weights in our model. This means that the feature extractor is not the right transfer learning strategy given the pre-trained model that we used, and that the deep network has actually learned features that are not easily transferable to Stanford Cars. This was really surprising to me personally, and really just goes to show that when you're modeling, you really just have to try everything under the sun. So when we pair optimization on top of the transfer learning process, we see a 4% boost in accuracy for ResNet 18 fine-tuned, and just over a 2% boost in accuracy for ResNet 50 as a feature extractor. This really just goes back to how fine-tuning is a better strategy for our problem, and adding optimization on fine-tuning allows the optimization strategy to essentially play with more knobs and be able to have more of an effect on the model versus when it's applied to a feature extraction strategy. Now let's take a look at how our model performance results correlate with how multitask optimization worked. So in the GIF above, we see how multitask optimization sampled the hyperparameter space for learning rate over the span of our whole optimization experiment. At the start of the experiment, we see small cost tasks exploring the hyperparameter space, with medium cost tasks coming in as the optimization is more confident of the area of the learning rate space to exploit. And then we conclude with just a handful of full cost tasks in like this one area of the hyperparameter space because the optimization strategy thinks that that is the optimal region, which is great. And this is what we would expect. We would expect to leverage cheaper tasks initially to kind of inform our more expensive tasks at the end. So we know how well the model performs. So let's take a look at where our best performing model, which is the ResNet 18 fine-tuned with optimization, actually fails, and what the misclassifications look like. So here we look at some interesting issues that we had with the model. Majority of the model's misclassifications are actually close calls. So like the Aston Martin example here, where the model either gets the make or the year mixed up. So here we see the actual label being an Aston Martin V8 Vantage Coupe 2012, and the predicted was Aston Martin Barrage Convertible 2012. They look like the same car to me, but they are actually different. But more interestingly, the model has difficulties classifying images when images are taken from unconventional angles, as well as when there's a lot of background clutter. One of my favorite misclassifications was this Hummer, where it thought the Hummer was a Volvo. Hilarious. Yeah, so overall, it's doing pretty well, but the problems it's having, we can actually hypothesize that it's actually related to how the data set is actually quite challenging, with the label space being very close and each class having a very low representation within the whole of the data set, which brings us to the next question: can we improve these results? And yes, we can. And the way we're going to approach improving these results is generating synthetic data using multitask optimization in this very simple loop. So essentially, we'll be introducing image augmentation as a part of our data pre-processing step, where SigOpt will now provide hyperparameter suggestions not only for image augmentation, but also for the model training. For the image augmentation process, each image will be augmented once and will go through horizontal flip, color jitter, be resized, and randomly cropped. The hyperparameters for the color jitter are saturation, hue, brightness, and contrast. And the parameters for these attributes will be suggested by SigOpt's multitask optimization. At the end of this augmentation process, we will essentially double our data set from around 16,000 images to around 32,000 images. And really what we're trying to do here is we're trying to beat our current best result. And we're trying to hypothesize or test our hypothesis that a lot of the problems our model is having is actually from this sparsity of data. So this is the baseline that we're trying to meet. It's the ResNet 18 model that we fine-tune and optimize, which is currently at an 87% accuracy, and we're going to introduce image augmentation to beat this result. So jumping into our optimization loop and what that looks like, SigOpt will now provide hyperparameter suggestions for color jitter attributes as well as stochastic gradient descent. Images will be augmented accordingly to the color jitter parameters. The model will be trained on the stochastic gradient descent parameters, and the validation accuracy will be reported back to SigOpt. So the model is going to be trained on a combination of the original and the augmented data, and the validation split will contain only the original data because we only care about how well it performs on our original data set. So what we see here, I think, is quite interesting. Through this relatively simple feedback loop, we are able to leverage a downstream supervised task, which is the classification problem, to make informed decisions on our upstream unsupervised task, which is our image augmentation process, which is pretty cool. So just as a recap for which hyperparameters we're tuning, we're going to be tuning SGD as well as color jitter. And here are the results. So if we just look at our standard ResNet 18 that we fine-tuned for our data set, we actually get a 10% boost in accuracy by including image augmentation and optimizing the model. And if we compare it to the baseline we're trying to beat, which is the middle bar, we actually get a 6% boost from that model, which is great. So clearly, like, including data really helped. And that really leads us to the question is, what did these like augmentations look like that led to this boost in accuracy? So here we have examples of the original image and the augmented forms of those original images. So the original is on the left side, and then the augmented is on the right side. And really what we see is the black box augmentation transforms the original image into like a super hyper vibrant form of the same image. The transformation applies heavy contrast to heighten the boundaries between the objects in the image. Similarly, a high level of saturation is applied as well to accentuate these boundaries and really differentiate the objects. So the power of these transformations is quite obvious in row 2, where we see the car going from being in the background of the banner to actually coming into the foreground, where for humans, I guess, as well as the model, it's actually more relevant as to like what is in the image. So in general, these transformations actually just accentuate the boundaries between the background and the foreground, as well as between objects in the image. So what did misclassifications look like this time around? So again, most of our misclassifications were close calls, like the BMW, and it still had problems with difficult angles. But we seem to have been able to solve the background clutter issues, and we hypothesized that that's because these augmentations actually do a really good job of differentiating the objects in the image, and maybe that actually helps with background clutter. More work would obviously have to be done to really know why the model prefers such augmentations for this data set. And there's a lot of work in general being done about robustness and understanding what the model is thinking. So why does this matter? Efficient optimization paired with efficient training techniques really allows any team to build high-performing models. And by including optimization earlier in the modeling process, we are able to get a better model performance, but also we're able to learn more about our data and about our model and really start to address problems of robustness and interpretability that I think a lot of people are generally interested in. So for those of you who haven't heard from us, at SigOpt, our mission is to accelerate and amplify the impact of modelers everywhere. In our experience, having access to the right tools for modelers can make the difference between success and failure. And our job is to make it more likely that you're successful. So thank you. And I will now take any questions that people have. Oh, there's one question. Is this the wrong URL for tuning data augmentation? I'm not really sure which URL you're referring to, but we will get on that. Oh, yes. So the presentation we wanted to do the backstory of like the data augmentation before we got to it as well. But yes, good question. So Matthew has a question. Did you try with just image augmentation without SigOpt? What was the accuracy achieved? I did not. I did not try that. I was really, so if we go back to this slide, I was really curious to understand, essentially, if we use SigOpt, which is kind of an active learning technique, what sorts of parameters would it suggest more than me kind of trying a different set of parameters and then running the model? And the thing is, like the reason for this feedback loop is the image augmentation data will actually have downstream effects on your stochastic gradient descent parameters as well. So this is just kind of a nice way to deal with both things at the same time. But yeah, I mean, this code is online, so it should be relatively easy to try this without SigOpt and just the image augmentation, but that's not something I did. But thank you for that question. Oh, yeah, sorry, Matthew, I just saw your other question. How does SigOpt recommend the mentioned parameters? Is it through some algorithm like Bayesian optimization? Yes, it is through Bayesian optimization. So SigOpt in general is a Bayesian optimization platform. So one of our features is multitask optimization, but our core thing is Bayesian optimization as a global ensemble of techniques. Yes, so the recommendation, so multitask optimization is an efficient form of Bayesian optimization, which comes from, goes back to kind of this example where this is Bayesian, but it's Bayesian based off of partially trained models, which makes it just a more efficient method to try that. Okay, so we have another question, which is, can data augmentation be applied to training data other than images? Yes, totally, it can. I think this simple feedback loop could be used for data sets that are similar to image data. So like maybe medical data sets, probably some regulatory issues with that. But I would be curious to know how well this would work for language data, for example, where generation is a whole problem on its own, let alone being used as an augmentation technique. So it would be really interesting to see how SigOpt would perform in as like parameters suggested for language generation prior to classification or sentiment analysis or NER. Okay, cool. We will send out the slides shortly after this webinar. All this content is also on the MLCon's website, so if you want to read the full analysis of the experiment, that's also a good place to do that. Well, thank you so much for joining me and us today. And those are great questions. So if you have any more, please feel free to like email the webinar link back or the contact. So we'll send all the slides out shortly. Thank you.